Hello and welcome back. In this lesson we are going to talk about specific heat capacity and latent heat. So let's get started. To understand specific heat capacity and latent heat, we need to understand what is thermal energy. In the image above you see still water in a jug. If you measure its temperature, it'll typically be the same as the temperature of the room you're in. Have you ever wondered what drives the temperature of the water in this jug? To understand that, let's see what's going on inside this jug of water. What you see on your screen is an illustration of molecules in motion inside this jug of water. And we know that objects in motion have kinetic energy, and this kinetic energy of the molecules inside water determines the temperature of water. In fact, the temperature of this jug of water is nothing but a simple average of the kinetic energy of all its molecules. The actual derivation of the relationship is outside the scope of the video, but it's important to know that the temperature of an object depends on the kinetic energy of its molecules, and it's a mechanism to express this energy. So, what happens when we pour water into a pan and put it on a gas stove? We know from experience that the temperature of the water is going to rise and eventually the water comes to a boil. But why? It happens because the gas stove is providing additional energy to the molecules inside the water, which causes the molecules to begin moving more rapidly, and this increases their overall average kinetic energy, thereby raising the temperature of water. This brings us to the definition of specific heat capacity. We define specific heat capacity of a substance as the amount of energy needed to raise the temperature of 1 kilogram of that substance by 1 degree Celsius. Let's take a few examples to understand this concept a little bit better. Here you see different materials with their specific heat capacity listed out. It's interesting to see that water has a relatively high specific heat capacity, and as such it requires significantly more energy to raise the temperature of water by 1 degree compared to that of gold or iron. Looking at this, we can draw a conclusion that good conductors have lower specific heat capacity as they easily absorb energy and their temperature rises. So now that we understand what specific heat capacity is, let's try to understand how it is calculated. We discussed earlier that when the kinetic energy of the molecules of a substance increases, its temperature rises. We can calculate that change in energy as the product of the mass of the substance, the specific heat capacity of the substance times, and the change in temperature of that substance. So we can write this relationship as delta E equals mc delta theta. Delta is a Greek word for change, so delta E means change in energy and delta theta means change in temperature. This relationship can also be used to calculate the value of specific heat capacity of any substance, which is then expressed as the change in energy of a substance divided by the product of its mass and the change in temperature. Now, here's a question for us to solve on this topic. It says, a home water heater stores 100 kilos of water and its thermostat is set to 60 degrees Celsius. On a cold winter morning, the room temperature is 15 degrees. Calculate the energy needed to heat the water until the boiler shuts down. The specific heat capacity of water is given. We know that delta E equals mc delta theta. Let's first find out delta theta, or the change in temperature. Let's now substitute these values in the equation. So, the value of delta E comes out to 18,900 kilojoules or 18.9 megajoules. That's a lot of energy. I hope this problem brings to life the concepts around calculation of the energy change when there is a change in temperature and how the specific heat capacity of the substance drives that. Now that we have covered temperature and specific heat capacity, let's dive into understanding what is meant by latent heat. To understand the concept of latent heat, let's briefly touch upon the structure of matter. We know that all matter is composed of atoms which bond to form molecules, which in turn bond to give structure to the matter. If we consider a solid, its molecules are very tightly bonded together, whereas in a liquid, the molecules are more loosely held. In a gas, the molecules are largely free to move around, and hence gases can expand and fill up any space. We also know that we can change the state of matter from solid to liquid and also to gas and vice versa. For example, ice is the solid state of water, which can be converted into liquid water, which can then also be converted into steam. Now please note this very carefully. Whenever a substance changes state, the underlying bonds between its molecules undergo a change. For example, to change the state of a substance from solid to liquid, the bonds between the tightly held molecules in a solid need to be broken, and for that energy is required. Now, in normal circumstances, when additional energy is supplied to a substance, it raises its temperature. However, something interesting happens when a substance is changing state. In that situation, the substance uses all the supplied energy to break the underlying bonds, while its temperature remains constant. That is the reason why substances have fixed melting and boiling points, because that temperature is a trigger for molecular bonds to undergo a change using the energy that is being supplied. This unique behavior of matter when it undergoes a change of state brings us to the definition of latent heat, which is defined as the amount of energy required to change the state of a substance without changing its temperature. This energy is expressed as the product of the substance's mass and its specific latent heat. To standardize this energy, we use a term called specific latent heat, which is defined as the amount of energy required to change the state of 1 kilogram of a substance without changing its temperature. And this energy required to change the state of a given mass of a substance is expressed as the product of the substance's mass and its specific latent heat. To understand this better, let's review how water changes state. Let's start with ice when water is solid. Now, ice in the freezer is typically at a temperature of -20 degrees. When it is taken out in a room where temperature is 25 degrees, the ice absorbs energy from its much warmer surroundings until its temperature rises to 0 degrees. At that point, which is the melting point of ice, it is still absorbing energy, but for a period its temperature remains at 0 degrees, and all the absorbed energy is used to break the bonds in ice to convert it to liquid water. This energy to break the bonds of solid ice to make it into liquid water is called specific latent heat of fusion, and its value is roughly 334,000 joules per kilogram. Once all the ice has liquefied, the temperature of water begins to rise again. This happens because at 0 degrees, water is still much cooler than its surroundings. Therefore, it continues to absorb energy until its temperature becomes equal to the room temperature, at which point there is no further rise in its temperature, and it is said to have reached thermal equilibrium, where its temperature is the same as its surroundings. Now, to change the state of water from liquid to gas, additional energy must be supplied using a heater or a gas stove. This additional energy raises the temperature of water until its temperature reaches 100 degrees, which is the boiling point of water. At that point, for a period, all this additional energy is used to break the bonds of water to turn it into a gas or steam, and until all water has vaporized, its temperature remains constant at 100 degrees. This energy required to break the bonds to convert water from liquid to gas is called specific latent heat of vaporization, and its value for water is 2.26 million joules per kilogram. The reverse process is also the same. Energy equal to the specific latent heat of vaporization is lost per kilogram of steam to convert it from gas to liquid, and energy equal to specific latent heat of fusion is lost for every kilogram of water to convert it into ice. We're all familiar with the freezer in our home fridge, which can freeze water. However, to convert steam to water, a condensation tube is used which cools down the steam as it passes through it, and water comes out the other end. Now, let's solve a problem to see latent heat in action. A container had 0.080 kilogram of water which was heated using an immersion heater. Once the water began to boil, it kept boiling, and after 10 minutes the container was weighed again. Its mass was now 0.071 kilos. A joule meter was used to measure the energy supplied during this period, and its reading was 25,200 joules. We have to estimate the specific latent heat of vaporization of water using this data. So let's solve this. We know that delta E equals m times L. Now, we have to find L, so let's make L the subject of the formula. Now we need to find the mass of water that was converted to steam in 10 minutes. We know we started with 0.08 kilos and the remaining water was 0.071 kilos. Now let's substitute these values in the formula. On calculating this, the value of L comes out to 2.8 million joules per kilogram, which is the specific latent heat of vaporization of water. So hope this problem gives you a better understanding of latent heat and how to calculate it. This brings us to the end of this lesson. Please practice a lot of questions on this topic and come back to the video if you get stuck somewhere. Until then, thank you and see you in the next lesson.